Today's session is going to be hosted by Ira Monkfold. He is one of our senior GIS engineers here at Phoenix LiDAR Systems. So Ira, go ahead and take it away.
Thank you, Lito. Well, hello all, and welcome to our May 2021 webinar. Today we'll be going over and trying to demystify some of the ideas about survey grade calibration, survey grade accuracies from point cloud data. This is a phrase that gets tossed around a lot, and here we are. I could dig in a little bit, uncover exactly what that means, and also uncover exactly how Phoenix LiDAR Systems can help you create this survey grade data. So here at Phoenix LiDAR Systems, we specialize in compact survey grade mapping systems with a variety of hardwares applied to a variety of platforms, and as well as that, aid the post-processing through many trainings and or a fully automated cloud LiDAR post-processing. Today, we'll be discussing about LiDARSnap 4, our most recent calibration tool. But here at Phoenix, we have been pioneering many different facets of this industry, from first commercial UAV LiDAR systems to vertical takeoff and landing systems, terrain following a flight planner, etc. We've been approached with many challenges. We have provided many solutions and are excited to do so into the future. So part of that is the challenge of survey grade data. While this seems like a pretty simple idea, really when it boils down, there's a lot of complications to it, and a lot of moving parts that are important to understand, to grasp, and to overcome in order to achieve this survey grade data. So let's achieve the survey grade data with LiDARSnap 4. This is our most recent calibration tool held within the Spatial Explorer software. So we will dive into a few different topics and then finish up with what LiDARSnap is and how it is actually going to accomplish some of these tasks and aid you in your projects. So we're going to go over three basic ideas. Try to demystify the idea of what is required for an accurate data set. How do you derive survey grade data? And how do you actually create that in a coupling of many different hardwares made through perhaps a software or three, and really how LiDARSnap 4 accomplishes all of this in a much more efficient and much more understandable way than many calibration tools in the past. So let's first kind of debunk, demystify, have a little better in-depth understanding of what point cloud accuracy is, what goes into it, what are the different factors that need to be weighed and understood so that you can move forward and progress towards actionable, deliverable data after every flight or drive. So big picture factors influencing our point cloud quality or accuracy really has three main categories. Our system, which is our combination of a GNSS antenna, an inertial momentum unit, also known as an IMU, as well as the actual LiDAR laser itself, all aboard some sort of platform, moving platform. For this presentation, we'll be focusing on aerial perspectives. So in system calibration, lever arms, which are the measurements in three different axes from the IMU center to the GNSS L1 phase center, seems like a lot of words, but fairly simple. In reality, the accuracy of this measurement, as well as the laser origin to IMU center lever arm, the accuracy of these measurements need to be impressively precise. If you're thumbing it to a centimeter type of precision, you can easily see multiple centimeter inaccuracies in your point cloud that is very difficult to overcome if these lever arms are not accurately input. Similarly, the boresight calculation of how your system is actually mounted together. If your laser is 1 degree rotated from where your IMU is, that needs to be addressed in a very, very precise manner. Half a degree difference shot over 1,000 or 100 meter laser range can result in huge inaccuracies. As well, once we pull all this data together, we end up creating a trajectory through the GNSS and IMU coupling. So the coupling technique and quality and attention to detail through that process has a huge influence on our point cloud quality, as well as a lot of the intrinsic IMU and GNSS parameters, such as GNSS quality, the angular random walk of our IMU, the IMU gyro bias stability, as well as a good understanding of the drift rate of the IMU from the rest of those parameters. In addition to the actual hardware on the rover while flying, our reference station is also of utmost importance. This base station that would sit nearby our project provides observation corrections for the rover. And so if this base station is logging incorrectly or is very far away, these observations are not corrected as much as they could be, thus degrading the point cloud quality. And on top of that, this seems like the most obvious one, but I say it last because these first two are of utmost importance as well, is the actual laser range data or laser quality. What's the actual laser accuracy and precision from the manufacturer? Laser wavelength has a huge effect on how laser interacts with different features and the precision from those features, as well as the beam divergence, number of returns, laser range, as well as the scan angle precision. All of these are very varied between different lasers and are important to understand and put in the back of your head while putting all of these multiple pieces of the puzzle together to understand what sort of quality your point cloud will have and what sort of quality or what sort of processes you will need to go through to create survey grade point cloud quality. Now, in these same general categories, we can talk about how we would improve the point cloud quality from their system or system boresight. So the calculation and refinement of those laser intrinsics, the misalignment corrections if the laser is mounted slightly off, tilt angle offset, which is the difference between how the laser and the spin axis actually in physical form is shown, range scales, as well as encoder calibrations. Many of these are not addressed by many calibration processes and calibration softwares. Most LiDAR calibration softwares simply stop at misalignment corrections and just go for a roll, pitch, and yaw correction and send you on your way. But in reality, there's far more physical nuances to these laser systems that need to be addressed, at least need to be understood so that you know if they do need to be addressed. And therefore, having a software that has the ability to understand and optimize these parameters is essential for survey grade point cloud quality. While if you have this perfect system boresight, this would create an ideal baseline for data collection. But every time a UAV or helicopter or whatever platform goes up in the air, flies, these, as we saw before from our middle column, there's many trajectory GNSS IMU reference station inputs that could undermine the system boresight. So that goes to our system optimization. Trajectory optimization, utilizing the point cloud is essential for mission-to-mission calibration. A little gust here, a slight overbanking of a turn there. These sorts of things are not overcome by a system boresight, but need to be looked at mission by mission and overcome in that way. There are many optimization techniques that we'll get into later, but these ideally would be able to optimize in any direction or orientation as the user decides. While we'll get into that later, most of the time that should just be a Z or up direction. Now, with the system boresight and mission optimization, while we are tied to a base station, we don't necessarily have a perfect relationship to absolute geospatial control. So that's where adjustment to control comes in, inputting surveyed ground control points and allowing the observations from this control to assign a linear shift, not rubber sheeting by any means, but a simple linear shift to GCP control points, then allows GCP checkpoints to then be used to assess this absolute geospatial accuracy. So now we've talked about how what's required to make an accurate data set. Let's go in and actually get into the factors of how we do this. How do we make a geospatially accurate point cloud? Now, as we said before, the system mounting boresight is essential. Here at Phoenix LiDAR Systems, we carefully utilize CAD drawings to measure offsets and orientations to the L1 phase center, as well as the antenna reference points of our GNSS antennas, as well as the precise IMU center of navigation that is the basis for all of these measurements. So from simple details, or seemingly simple details, like ensuring the center of gravity is established for a given platform, the IMU to GNSS lever arm could change if that center of gravity is adjusted. So understanding that and overcoming that is essential. Similarly, with the IMU to LiDAR lever arms, those need to have high precision and very detailed, careful integration. Not just slapping an IMU and a laser together and putting it up in the air. These need to be done very carefully and precisely and ensure that they will have repeatability through many, many missions and many years. Understanding how the vibration isolation is conducted on your aerial platform is essential as well. And once again, per laser translations, as multi-laser systems have different locations for their various lasers. But let's go ahead and jump into the laser intrinsics, which is really where a lot of the meat and potatoes of LiDAR calibration come in. System boresighting is relatively easy to understand and compute, especially if you have well-developed drawings, or maybe even a TLS scanner, a terrestrial LiDAR scanner, to really map out how the system is put together. Fairly simple ideas. Now, some of these larger concepts like tilt angle offsets, which is the angle between the laser and the spin axis, could be ever so slightly different as it rotates. And this kind of offset isn't really overcome with a rotational correction, as that doesn't change or doesn't correct the relationship between the spin angle and the laser angle. Things like that, range scale, a multiplier onto the range for certain scanners that have been known to have slightly inaccurate range. Luckily, they are often very consistently inaccurate, so we can correct for that. Scan angle scale is sometimes of importance to different scanners that either smile or frown on the outside edges of their scan angle. And almost most importantly, or very important for certain scanners, is an encoder calibration. As some sensors don't have their encoder mounted quite properly, such that the center of the encoder doesn't quite match the center of the spin axis, thus introducing error as it spins. So we are able to overcome this with very careful, very complex mathematical models. Up on the top right, you can see the start and end calibration process through LiDARSnap, where we have fairly large offsets between different strips at the beginning on the left, and then refining to a very high level of detail on the right, using the calibrations you see at the bottom. Now that we've gone through our system boresight, system intrinsics, let's now talk about our individual missions. Now these individual missions, as I said, could be gusty here, maybe Maybe a quick GNSS issue here or there. Maybe flew by a big building and lost satellite count. Very weird things can happen up in the air. And that's why it's very important to have the tools in your tool belt to be able to overcome these issues when they come up, rather than be blindsided by them when they do. That is why it's very important to understand all of these concepts and really understand what these different parameters, these different optimizations, these different calibration processes are doing for your data and why. So for trajectory optimization, as most of us know, the GNSS antennas are often extremely accurate in X and Y and tend to have the least amount of accuracy in the Z direction. So our trajectory optimization allows for us to correct for these Z inconsistencies, inaccuracies. Although we are coupling our GNSS and IMU data through either NavLab or Inertial Explorer or some other outside entity, while NavLab is embedded in Spatial Explorer, these trajectory optimizations can happen anywhere. Many of the inaccuracies are mitigated, but not to the complete, not to the level of detail that they could be. These softwares just deal with the GNSS, IMU, and base station data and have no relationship to what the point cloud is, the laser data, or really any relationship between the trajectory and point cloud data. So by relating the trajectory to the point cloud in LiDARSnap 4, this really aids the optimization of the trajectory because in reality, the trajectory is important, but the point cloud is what we're ultimately delivering, what we ultimately need to be in survey grade accuracies. Now, once we have our mission, our system and our mission relatively locked in, let's lock this project into ground control. And this is the final step of accomplishing a survey grade point cloud deliverable. Ground control point adjustment really allows us to input surveyed ground control and either utilize these ground controls as check or control points. The control points are used as observations to compare to the point cloud, and then an adjustment, a vertical adjustment, a linear vertical adjustment is calculated from all of these different observations. Once the point cloud has been adjusted to this control, and in LiDARSnap 4, we also adjust the trajectory to make sure that relationship stays consistent. Then our checkpoints are used to actually assess the absolute accuracy, provide our RMSE-Z final absolute accuracy metric, and really allow us to do it in a lot of confidence, since these checkpoints are never used as control points, or never used to derive a shift. One essential part of this process that is often overlooked is the exact matching of projections and datums from your ground control file or your surveyed points, whatever it may be, to your point cloud. This relationship is often where this process falls through the cracks. And one wonderful thing about LiDARSnap 4 and Spatial Explorer is because all of these files are held within the same software, we're not jumping around between different softwares, we're able to really control the datum projection of our project so that all of these match and relate to the way they should. So as I let the cat out of the bag, LiDARSnap 4 can do all of these processes above in one step, from calibrating boresight and sensor intrinsics, optimize trajectory or trajectories, and adjust to ground control points, or even a control cloud if you had a reference cloud that you needed to match to. LiDARSnap 4 does all of this in one dialog in any multitude of stacked steps, or simply one at a time if that's what the user desires. Result of this, as somebody who has transferred files between a dozen different LiDAR processing softwares and has watched that little green bar run across my screen far too many times, having all of this in one software, in one step, really saves time. And really, on top of that, which is kind of more important to me, really makes our data outputs trustworthy and consistent. Through having all of these steps in one, you have ultimate control and observational quality of these different parameters and what the results are. They result in survey grade point cloud accuracy that's geospatially correct and relatively and absolutely aligned with itself. Another wonderful result that automatically pops up is a in-depth report that we'll get into a little bit later. We also get an optimized trajectory output that's adjusted to the ground control and adjusted through its trajectory optimization that then is able to be output if desired. And really, what it all boils down to is this is an excellent return on investment. For one subscription fee, one software, one place to stop, one place to start. It really streamlines the whole process of LiDAR calibration, which many of us know can be quite cumbersome, quite time-consuming, and quite a headache and a burden on our team. So let's go into a lot of the benefits of LiDARSnap 4. Let's start off with the boresight back again. While normally traditional boresighting is done just with mounting translation rotations, LiDARSnap 4 also utilizes these encoder calibrations. So the center of the encoder not matching the spin axis, as well as the angle of the laser and the spin axis perhaps being slightly off. LiDARSnap 4 allows us to very carefully calculate and calibrate those parameters that are inherent in every laser system, but not necessarily addressed in every LiDAR calibration software. Because these are physical mechanisms causing these laser errors, we have developed fairly complex mathematical models to implement into LiDARSnap 4 to calculate these intrinsics. And wonderfully, in calculating these intrinsics at the same time, we're able to then relate that to the translation mounting, the rotations, so that we are not chasing our tail in multiple stepped calibrations. Nobody wants to calibrate their rotations to then calibrate something else to then find out that those rotations are no longer valid. So doing this all in one step provides the utmost in time saving and increase in accuracy. We're also able to optimize our trajectory through 4 different optimization models. Bias, linear, spline, efficient, and full. Utilize different algorithms, have slightly different applications, where linear would be very helpful for long helicopter missions, spline efficient for very quick UAV type missions. But we can get into that in a future webinar, or you can also visit our website and check out some of our Spatial Explorer 6 videos, and also visit our user manual online, which explains these a little bit more in detail. But we're, once again, instead of simply just doing a GNSS IMU coupling technique, utilizing our base station observations to refine this trajectory, we're adding on to that by allowing the point cloud to determine optimizations for the trajectory as well. These observations that we're using for our boresight and intrinsic calculations are also going to be used for the trajectory to optimize in really 6 different ways if the user desires. Up, down, or rather up, left, forward, roll, pitch, yaw. Whereas, but as we said before, most trajectory optimization is ideally done in just a Z direction. And also ground control. We're able to bring in ground control from a multitude of files. These ground control files can be in different projection systems, so long as the user knows. So you get control from 2 different survey companies. One uses ellipsoidal height, one uses orthometric, one is living in a UTM zone, one is living in a local state plane zone. These can be utilized at the exact same time in the exact same project because Spatial Explorer 6 has a project datum and projection. It will then bring those different projections back into its local project coordinate system. So not only can we bring in ground control files, such as CSVs, we can also use a reference point cloud for vertical adjustment. And as you see on the right, we're also able to manually edit which points are control points and which points are checkpoints. And there is a plethora of reporting and information and visualization you can do to then see where each point is, what its residual to the point cloud is, and really be able to QA/QC some of those points. So through the association of the point cloud to the control points in this step, a vertical shift is applied to the trajectory, which then is applied to the point cloud, and also a absolute accuracy reporting using the checkpoints, the QA/QC checkpoints, is also derived and given to the user in an HTML format. And once this one-step calibration tool is completed, we actually provide quite an in-depth report showing hardware details, acquisition details, the relative accuracy of the point cloud, so line to line, how does the point cloud relate to itself, as well as the absolute accuracy as how the point cloud corresponds with the checkpoints. These correspondence errors are visualized in histogram as well as a few different other plots. And also you're able to understand what type of observations were used in which direction in the normal observations plot to ensure that you're not analyzing the point cloud solely from a roll perspective or a pitch perspective. You have a good a wide range of observations to correct from. This in-depth report really gives you a lot of peace of mind as this report is consistent every time and it's automatically produced. This really enables you to know that every project you do will have very similar results, very similar reporting, and really really automates a lot of this process. Not only giving you the peace of mind, but also the time saving. And just for people like myself who love reports and all, but I really need to look at some points and spin some clouds around, as we all find ourselves doing from time to time. Spatial Explorer 6 has wonderful visualization tools, very smooth .cloud file format that allows for rendering of gigantic point clouds if necessary, as well as a multitude of visualizations from color to GPS time to intensity. Really any attribute of the point cloud can be utilized to visualize. And then we can make measurements, do cross sections, toggle between different visualizations to really make sure that we are seeing the point cloud that our report is describing. So what this all boils down to, and I have seen many LiDAR calibration tools, softwares, algorithms, methodologies, and most of them work fairly well, some of them better than others, some of them take far longer than others. But really what LiDARSnap 4 does is creates one software, one cost, and a very quick, very easy to use module for LiDAR calibration. The stacked processing of this to allow us to not only calculate laser intrinsics, but also trajectory optimization while also matching to ground control by clicking a button once and having all of these processes happen simultaneously. It saves a tremendous amount of time and also really really makes it very easy to cross-train, very easy to train in the beginning, which once again will save you time and money as years go on, and you have to pass these workflows and methodologies on to the next round, or maybe a new employee. Not spending a week training somebody on the software, but maybe a few hours can greatly reduce your cost, greatly increase your return on investment, and really make this less of a headache for everybody involved. Speaking of less of a headache, simplicity is one of my favorite words to say in a webinar like this, as that is a very rare thing to be able to say in a webinar like this. But wonderfully, LiDARSnap 4 really does give us that. Having all three of these main factors all in one dialog, just a couple tabs to cycle through. We also have a very user-friendly online user guide that's constantly being updated. These parameters are detailed well in that user guide. And also they're fairly logical in the actual user interface. And one thing I keep coming back to as a experienced user is just the consistency and the quality of results. Not only the consistency of your reporting, but the consistency of your point cloud data, and really being able to trust this process to provide us with a survey grade point cloud. As I said before, the internal cross training becomes a breeze. In fact, instead of having your boss come over and just spinning a point cloud in front of them, they might be able to look at this and have a more in-depth understanding of what these LiDAR systems are, what they can do, and what the parameters are that go into them. So maybe you're going to be cross-training that way. Who even knows? You might have that much fun. But really, the simplified, streamlined simplicity of this module is really what shines and really what provides that return of investment. I've responded to many RFPs in my days, hoping that we would be able to pull it off. With this LiDARSnap 4 and the consistency of results and the ease of use, responding to those RFPs with confidence, knowing that this data is going to adhere to requirements is such a huge peace of mind. That plus useful reporting really aids our end user confidence. Also, because we're not jumping between different softwares with different file format ideas, different header overwritings, having all of your data come from a single software really streamlines a lot of that headache that can kind of come back and bite you after delivery. So I very much encourage you to come visit our website, come contact sales, check out some of our Spatial Explorer 6 videos, some of which include this LiDARSnap 4 module. And really, I'm excited for everybody here to dive into this LiDARSnap 4 and really realize how much benefit this can provide each and every user, from the smallest data set and the smallest clients to huge government entities or corporations that need very consistent, very rapid data deliveries. LiDARSnap 4 can do it all, and do it all with great ease for you and your team, really doubling down on the return on investment and the cost savings that you're going to get from this module compared to 3 different high-end LiDAR post-processing softwares, all competing with each other with different subscription fees and maintenance fees and trainings and headaches and headaches and headaches. So I'm very excited for everybody to see LiDARSnap 4, to use it, to really benefit their end deliverables and end clients with survey grade data deliverables. With that said, I'd love to open this up to any QAs, any questions. I'll probably deal with the answers, but I might have Ben or another colleague hop in. So let's open the floor.
Yeah, we do have a few questions here that can go to either you or to Justin Wyatt or to Dr. Ben Adler, our illustrious CTO. First one here I have is LiDARSnap 4 an alternative to IE? And if so, what are the advantages of using IE or LiDARSnap over the other one?
We still recommend doing a IE type, inertial explorer type post-processing of our trajectory, coupling the GNSS and the IMU data while getting refinement to the GNSS observations through base station observations is really a key first step to creating quality point cloud data. With that said, Spatial Explorer 6 has our NavLab embedded into so we can access the internet, upload trajectory files, upload GNSS and IMU information, base station information, and have a very similar post-processing of our trajectory hosted by the cloud that then can be brought right back into Spatial Explorer as we hadn't even left that software and then utilized in LiDARSnap 4.
Justin, can you speak more to the relationship between SE Pro and NavLab / Slidermill?
Yeah, so we have a lot of softwares that we offer our clients that can help manage some of these tools and workflows for LiDAR processing. In this, what we're featuring today is the ability to work with Spatial Explorer Pro. It's our newest version of software. And this LiDARSnap component is a component of Spatial Explorer Pro. NavLab is a trajectory-only processing software. And Slidermill, by contrast, is a kind of front-to-end processing software that exists in the cloud. That's a very high-level overview. The integrations are somewhat overlapped. And so I'd be happy to take some specific questions to that to drive down a bit deeper. Or take your emails privately and give you guys tutorials and maybe even some limited access into the software suites to give you guys a free trial.
Okay, so for the trajectory post-processing, the PPK, we do have the option of using either Inertial Explorer or NavLab on top of LiDARSnap 4 to get the ultimate in calibration. Next question I have here is, can I calibrate data from multiple flights at the same time?
That's a resounding yes. Yes, we can input multiple trajectories into LiDARSnap 4, and this entire process is multi-trajectory compatible.
Great. Okay, another question here. Does this work for large, wide area projects collected from a helicopter platform? I know you're focusing on UAVs for this presentation, but what about helicopter collected data or other manned vehicle collections?
Yes, this will, Spatial Explorer 6 and LiDARSnap 4 are perfectly compatible with larger data sets. The .cloud file that we utilize to create and alter and optimize our point cloud is cached in a way that allows really an infinite size of .cloud file. Obviously, infinite size file is kind of a silly phrase, but you get the idea that this can be as big as it needs to be. I will have to say a very large helicopter-based wide area project is going to take much longer to process, but I think that's a given as well. But yes, this Spatial Explorer 6 Pro and LiDARSnap 4 deals with scales very easily.
So along those lines, what kind of processing times are we actually dealing with from calibration to perform calibration from LiDARSnap? If you can give some sort of scale reference, that would be appreciated.
Yeah, I would say a single UAV flight, let's say a 15-minute flight covering, shoot, what do we say, like 10, 20 acres? Well, let's just say a single 15-minute flight. Obviously, the acreage is dependent on the scanner and the flight height. But a LiDARSnap 4 processing with trajectory optimization, laser intrinsics, and ground control assessment and reporting, LiDARSnap would probably be done in about, let's see, I'm also thinking about my archaic computer, but I think probably about 10 minutes, 15 minutes. The reporting may take another 10 minutes on top of that to calculate the residuals, but really pretty quick. If we're going to the scale of multiple hour helicopter missions, this might run up into the hour or two type of scale, but this is also very computer dependent, making sure that you're on a local solid state drive rather than a spinning network drive. Those sorts of factors certainly play into it, but in terms of the speed, and especially compared to other softwares that I've seen, it is very fast.
Okay, here's another question. Are there any limitations on what kind of systems we're able to use LiDARSnap? Any limitations to manufacture or multi-beam versus single laser?
LiDARSnap works with both single laser and multi-laser systems. It has to because we sell them. And of course, we use LiDARSnap to calibrate our systems before we ship them. As for other manufacturers, so long as we can import the data, be it a LAS file or even raw data for some, then yes, we can. I'm sure there's others that we cannot, and really depends. We would need a sample data set to determine that.
And here's another question that we actually often hear. Can LiDARSnap 4 be used to calibrate other LiDAR mapping systems outside of ones that are purchased from Phoenix?
Oh, maybe that's the question I meant to answer. So yes, as long as we can import that, like if you can export to anything standard, say an SBET and a LAS file, then yes. And yes, there is some raw data we can also open. Again, really depends. So please send us a sample data set and we see if we can process it.
Okay, and I do have one more question here, and I think it's a little asking for a little bit of clarification. Is LiDARSnap part of LiDAR's SE Pro Spatial Explorer Pro Basic, or only a part of Spatial Explorer Pro?
Really a sales question, but I'll try and answer. It is part of SE Pro. It's not part of the free Spatial Explorer that comes with our systems.
Okay. Okay, that's all the questions that I've logged here. Ben or Ira, do you have any closing comments anything else you'd like to add?
I would just like to say thank you to everybody. I appreciate the attention and all the good questions. And I'm really excited to see people kind of jump into this and get a hold of Lido and get a hold of sales here at Phoenix and see what this can do for you. I am pretty confident that majority of users, whether they have an established workflow or not, can find benefit in LiDARSnap 4.
And if you have any questions for our sales department, if you're already a Phoenix customer, please contact your rep. Or if you're not, then feel free to contact sales@phoenixlidar.com. Come to our website, which is phoenixlidar.com. And if you'd like to see a replay of this session, or if you'd like to share it with your colleagues, again, go to phoenixlidar.com, go to the News tab, and you'll find a link there to request access to replays of any of our webinars. Once again, thank you very much, Ira. I appreciate it. Thank you very much, Ben. This has been the May 2021 Phoenix LiDAR Systems webinar, and we look forward to seeing you next time. Thank you very much.